Okay, now we're going to do the last part of the 7.3 worksheet. The last part is called limiting reactants. All right, limiting reactant means what? Now, let's just talk about a normal chemical equation. Let's say a chemical equation has got X and Y, right? So you're going to react X and you're going to together with Y. So how much X are you going to add and how much Y you're going to add? If you do not know, you just anyhow add one of the X, either X or Y, one of them will be completely used up while the other one will be excess. Okay, one of them will be completely used up whereas the other one will be excess. So let's highlight this. There will be an excess amount of one reactant while the other reactant is completely used up. Okay, so the two words to know, excess, and the other one is completely used up. Surely one. Very hard to know exactly how much X will react exactly with how much Y. Very difficult. So normally you just throw in some amount. One of them will be used up, the other one will be extra. Now the one that gets completely used up is what we call the limiting reactant, and it's the important one. Okay? It determines the amount of products formed. It's the one that decides how much product will be formed. The excess, we don't really care. Okay? Now, let's explain further. Let's say you have this equation. You have H2 plus Cl2 giving you HCl. What is the mole ratio based on this equation? Mole ratio is 1:1:2, right? 1:1:2. That means that 1 mole of H2 reacts with 1 mole of Cl2 and then 2 moles of HCl will be produced. If you manage to actually react, you have this correct amount, then all the reactants will be used up because you are using the exact amounts that is needed for the stoichiometric proportion, 1:1:2, if you use exact. What happens if we don't use the exact amount? So what happens if we react 1 mole of H2 with 2 moles of Cl2? Now comes a more interesting question. So let's look at this part now. So at the start of the reaction, what do we add? We add 1 mole of H2 and 2 moles of Cl2. But there's no product yet, all right? Because the reaction just going to start, haven't started yet. At the end of the reaction, what will be left behind? Okay, the 1 mole of H2 will be completely used up. How much of the chlorine will get used? Only 1 mole, all right? Only 1 mole of chlorine will be used up because remember our stoichiometric proportions? We said that, we said that it's 1 mole is to 1 mole is to 2 mole. That's what the mole ratio says, right? The mole ratio says 1 mole is to 1 mole is to 2 mole. So every 1 mole of hydrogen will react with only 1 mole of chlorine. But we have 2 moles of chlorine. So 1 mole will be unreacted. 1 mole will be unreacted. Oops. Okay, 1 mole will be unreacted. What is going on? So now got product ready. 2 moles of product will be produced. Okay? So why is it important to know what is the limiting reactant? So because it's the one that's going to get completely used up, we will ensure that the limiting reactant will be the more expensive reactant. Okay, it will be the more expensive reactant. So we need to know the limiting reactant to get the maximum yield of product at minimum cost. And therefore, we will choose the most expensive reactant to be the limiting reactant. Okay, the most expensive one, we make sure it's the one that it will get totally used up. Right. Now, as we said already, the amount of limiting reactant will determine the product. How much product you get depends on how much limiting reactant you use, right? How much product you obtain is determined by how much limiting reactant you use. Okay, next. So, what is the limiting reactant method? It's similar to MRU, alright? Similar because you are still finding mole, but this time you are finding mole for both reactants. Okay, for both reactants. After that, you still find mole ratio. Okay, that's the same. And then, when you find mole ratio, use the smaller mole value into the mole ratio. Use the smaller mole value. Okay, we will know that when we do the example. And then the third step is deduce the limiting reactant and the reactant in excess. Again, we will see that in the example. Right, let's start straight away, go to the example. The reaction between zinc and sulfur produces a large amount of heat. Our first number we got already. 13 grams of zinc. Okay, 8 grams of sulfur. So it's zinc and sulfur. Zinc and sulfur. Identify the limiting reactant. So method says that find mole for both reactants. That's the first step. So that's what we are doing. In our answer, find mole of zinc. What is the formula we're going to use? Mole equals to mass over MR. So it'll be 13 over 65. We get this value. Okay. Then after that, same thing for sulfur. You get 0.25. Now, so you find mole already. Next step, find the mole ratio. Okay, find mole ratio. Put in the smaller number. So between 0.2 and 0.25, the smaller number is 0.2. Alright? Even if you put to 0.25, it won't be wrong. But it's nice to just remember 1. Alright, use 1. So, mole ratio will be 1:1. But now we're going to substitute the 0.2. The smaller one into here. Okay, 0.2. Then how much will the sulfur be needed? Then you find that, we only need 0.2 moles of sulfur. Okay, but what did we have in the first part? We actually have 0.25 mole of sulfur. That means that, but out of the 0.25, we only need to use 0.2. That tells us that sulfur is therefore in excess. Okay, sulfur is therefore in excess. Excess by how much? How much is the extra? How much didn't get reacted? So, unreacted sulfur, take the 0.25 minus 0.2, we get 0.05. And that's the mole, correct? Now we want mass, so just convert and we will get 1.6 grams. Okay, identify the limiting reactant. So the limiting reactant is zinc. Is that okay? So we are done. Okay, that is the example. So follow this same method. Now let's look at a question. In an experiment, 4.0 grams of sulfur, highlight, will burnt in 48 dm cube of oxygen. Okay, So grams, so this tells us is a mass. 48 dm cube tells us is a volume of gas. Oxygen is a gas. What was the limiting reactant? So what's our method? Number 1, find mole for both. Okay, so mole equals to mass over mR. So it will be 4 grams over sulfur is 32. This will give us 0.125 mole of sulfur. So we have calculated sulfur. Then the other one, mole of oxygen. Okay, oxygen now is a volume. So again, what's your weapon? What is the volume formula? Which mole formula has got volume one, not mass anymore? So it will be volume of gas over 24 dm cube. So it will be 48 over 24. This will be 2 mole. And this time this is for oxygen. So we find mole for both already. How do you know which one is the limiting and which one is in excess? You know that by taking the mole ratio. Compare the two of them against the mole ratio. And we don't have the equation. Mole ratio comes from equation, so we have to write our own. Sulfur plus oxygen will give you sulfur dioxide. That's what the question says, right? To form sulfur dioxide. So we write our equation. Mole ratio is actually 1:1. S is to O2 is equals to 1:1. Now, what do we have from first part? Take the smaller of the two numbers. So sulfur is 0.125. That means that mole of oxygen needed is also equal to 0.125 mole. But how much mole of oxygen do we need? But how much mole of oxygen do we have? But we have 2 moles of oxygen. Therefore, we can say that oxygen is in excess. We only need 0.125, but we have 2 mole. So oxygen is in excess. Therefore, the limiting reactant, that's what the question wants us to find, is sulfur. This is our answer. Okay, that's our answer. The limiting reactant is sulfur. Okay, next. Calculate the volume of sulfur dioxide. Now our unknown is sulfur dioxide. We don't have any value, any information about sulfur dioxide. When you don't have anything about sulfur dioxide, you must go and find mole ratio to connect this sulfur dioxide to something that we know. So we have to connect it to sulfur. Okay, why? We have to use the limiting reactant for further calculation. Use limiting reactant, not the excess. Use the limiting reactant for further calculation. So, mole ratio, sulfur is to SO2 is still 1:1. And since the sulfur, we have how many moles of it? Sulfur is how many moles? Sulfur is 0.125 mole. Sulfur dioxide will also be 0.125 mole. Okay, now we can convert it to volume. We know the mole already, now we convert it to volume. So what's the equation for volume? Mole will be equals to volume of gas divided by 24 dm cube. Okay, so volume of SO4, SO2. Volume of SO2 will be equals to mole times 24. And that will give you 0.125 times 24, 3 dm3. Okay? So that's how we do it. Limiting reactant, similar to MRU. Okay, number 2. Let's look at the question. Ethene burns in oxygen according to the equation blah blah blah. Straight away take note, they are all gases. Do you still remember the formula that we can use if they are all gases? Right? All gases use mole ratio is equals to volume ratio. Okay? So which gas was supplied in excess? So let's always start with mole ratio. 10 cm³ of ethene with 50 cm³ of oxygen. So go and find these two. Ethene is this one, and oxygen is this one. Correct? So it will be equals to C2H4 is to 3O2. 1 mole is to 3 mole. Then mole ratio equals to volume ratio. That means this is 1V is to 3V. Okay? So how much ethene is there? Ethene is 10 cm³. Okay? Therefore, oxygen should only be 30 cm³. Only 30 cm³ of oxygen is needed. Volume of oxygen needed is equals to 30 cm³. Okay? But initial volume of oxygen, at the start is 50 cm³. Therefore, oxygen is considered to be in excess. That is our answer for the first part. Which gas was supplied in excess? Oxygen is in excess. Okay? Next, calculate the volume of the excess reactant at the end. So when it ended, how much oxygen will still be left behind? Volume of excess O2 will be equals to 50 minus 30, 20 cm³. So 20 cm³ oxygen will still be left behind. Last one, calculate the volume of carbon dioxide produced. So carbon dioxide, we have no information about carbon dioxide at all. So therefore, we have to relate it to something we know by using mole ratio. Okay? So don't use the excess reactant. Remember, we have to use the limiting reactant. So use the limiting reactant for further calculation. So it will be C2H4 is to 2CO2. Don't use excess. Oh, what happened? Sorry. Is this the one? No. Hey? Okay, all disappeared. Hiya. Okay. So let's go back to this. Okay, whatever I wrote disappeared, so therefore we are going to just continue from C. You should have written it down. So use limiting reactant value for further calculation. So mole ratio will be equals to C2H4 is to 2CO2, which is equals to 10 cm cube is to 20 cm cube. Okay, therefore volume of CO2 produced, volume of CO2 will be equals to 20 cm cube. And we're done. Is that okay? Okay, next. Question 3. Alright, question 3 is the last question already. Do it yourself. Do it yourself. Pause the video and attempt it yourself. Okay, pause the video, attempt it yourself. Okay, this is the model answer. So, we are asked to calculate mass of sodium chloride. This is our unknown. And what are we given? 53 grams of sodium carbonate. Okay, something else. You are asked to calculate sodium chloride, but you are given sodium carbonate. Whenever you see this is MRU method. Okay, so part 1. Mole of sodium carbonate, Na2CO3. Find mole, right? Find mole. First thing, always find mole. So it will be 5 mass over mR. This will be 5.3 grams divided by 106. And this will give you 0.05 mole. Okay, M done. Now second part, mole ratio between Na2CO3 with sodium chloride, because these are the two things that I mentioned. And from the equation, there should be a 2 in front of the NaCl. Okay, from the equation. You can see here. Here and here. Okay? So it's 1:2. But from the first part, Na2CO3 is actually 0.05. How much will be NaCl? So mole of NaCl is equal to 0.1, because it's 1:2. Thirdly, third step, find the unknown. So our unknown is mass. Alright, so lastly, okay, I better not put the numbers, otherwise it's like, so mass of NaCl will be equals to mole times mR. 0.1 times 23 plus 35.5. Answer is 5.85 grams. So part A done. Part B. 53 grams of sodium carbonate, so this one is mass, was added to 700 cm cube. That one is volume of HCl. And 2 moles per dm cube, that's concentration of HCl. What is the limiting reactant? So limiting reactant, we need to calculate, find mole for both. Alright, find mole for both. So mole of Na2CO3, I'm going to cut short a lot already. It'll be equals to mass, which is 53 grams, divided by mR, which is 106. So this will be 0.5 mole. How about mole of HCl? How much is that? We are given V and C, volume and concentration. Formula to use will be C times V, which is C is 2 times 0.7, okay, dm cubed. This will give us 1.4 mole. So we have the two moles. Now, we got no space to actually do the rest of the working. So I'm going to squeeze it in, okay? What is the limiting? So now you have to take the mole ratio, okay? Mole ratio, Na2CO3 is to HCl, okay? And from the equation, it'll be 2 HCl. So it's actually 1:2, correct? But if we have 0.5 of Na2CO3, then HCl will be 1 mole. We are going to need 1 mole of HCl, okay? But how many moles of HCl do we have at the beginning? It's supposed to be 1 mole, but at the start, we have 1.4 moles HCl. Therefore, HCl is in excess. Okay, limiting reactant is Na2CO3. That is our answer for part 2. Okay, last part, calculate the volume of carbon dioxide formed. So what is the volume of carbon dioxide? We need a new mole ratio because we have no information about carbon dioxide, and we have to use the limiting reactant, okay? Mole ratio of the limiting reactant, which is our Na2CO3, is to CO2. From the equation is 1:1. But we have 0.5 moles of this. How much CO2 will be needed? Also 0.5. Okay, but we don't want moles of CO2. We want volume of CO2. Our unknown is volume of CO2. So how much is the volume of CO2? Volume of CO2 is equals to mole times 24 dm cubed. 0.5 times 24, and this will be equals to 12 dm cubed. So we have calculated that. Okay, wait, so this is part 1 and this is part 2 because we ran out of space. Okay, and with that we have finished this part here. Next, I'll be letting you try some 10-year series questions, like so what kind of questions will come out in the exam. Is that okay? Right, we'll stop here for now.